quick note, if you'd like to ask a question, please use the chat box you see on your right-hand side to enter the questions, and we will read the questions off at appropriate times. Again, this is James Meldrum, a postdoc at the University of Colorado Western Water Assessment, who's going to be presenting, and I will turn it over to him right now. Take it away.
All right, thanks, Eric, and to all of you for tuning in or showing up today. So first, some brief outline of what I'm going to go over. Start with some energy water basics and talk vaguely, generally about electricity generation technologies and water use. From there, I'll move into discussing baseline assessment, looking at where things are today. So looking a little more details into technology choices and the present day water use. From there, I'll move on to discussing a little bit about future assessment. Talk about multiple approaches to modeling the way energy and water choices might look in the future, and go over some common themes and storylines. And in between each of these sections, I will address any questions that you've typed into the chat box. And so kind of what I hope for this is it to be a two-way information sharing process. So basically, I'm providing basic information on water electricity issues and some of the modeling related to future trends. And I really do hope that you'll be able to provide me feedback not only on the information and the approaches described, but also on the interpretations and future directions of this work. So first, some background on me and the cast of characters involved. I finished my PhD in interdisciplinary environmental economics from University of Colorado in Boulder Environmental Studies program last May. I've been involved with Western Water Assessment since then, as Kristen Avert has moved on to her new role as Associate Science Director for CERES, the Cooperative Institute for Research in Environmental Sciences. The work I'm doing here dovetails with work I've done with the National Renewable Energy Laboratory with Jordan Macknick and Garvin Heath on estimating life cycle water use for electricity generation, as well as my more general interests in decision-making about natural resources, relationships among resilience, efficiency, and sustainability. So the material that I'm talking about today draws extensively from a team of researchers who's contributing to the Union of Concerned Scientists Energy and Water in a Warming World Initiative, which I'll be referring to as EW3. And as you can see here, the list of researchers is people from a variety of institutions, Stockholm Environment Institute, National Renewable Energy Laboratory, and the Union of Concerned Scientists. And this group is driven or guided by a science advisory committee, and this committee consists of basically an all-star cast of people who are involved in energy water research. So that said, what I'm presenting today is preliminary analysis and things that are in various stages of peer review. So it's important to recognize that I'm speaking for myself and not necessarily for all the people listed here, even though I'm showing a lot of their work. So the way this initiative is working is there's a focus on both what are referred to as public-facing documents, which the first is this report released in November 2011, which you can access on the Union of Concerned Scientists website. And this is the first part of what I'm going to be talking about, this baseline assessment of how do we use water in electricity generation today, and what are some of the technology choices and the implications of those. And then there's going to be a second report slated to come out in May 2013 that looks at a lot more of the future modeling and some of the more broader implications. So a lot of the work that I'm talking about is represented in these. It's also aimed for, in the academic literature, a special issue to Environmental Research Letters, which is an academic journal, and the special issue is titled Electricity, Water, and Climate. And the initial papers for this are going to be released in December 2012 with rolling release for a lot of the other papers. So the vast majority of the work that I'm talking about and referring to today is at some stage a peer review process for that journal. And I'll note, of course, where these things can be found later. And then finally, a large contingent of the EW3 group is going to be coming to the American Geophysical Union at the fall meeting in San Francisco in December. So if you happen to be there, come look up some of us to find out more information. So with that, I'll move on to the content of today. So basically, the underlying theme or topic to this all is that energy and water are intrinsically linked. It takes energy to move water, and water is required for generating electricity. So nationally, roughly 41% of water withdrawals are to generate electricity through some sort of thermal process. A smaller portion of this water is consumed, but the amount of water that is being consumed in the sector is increasing while it's relatively stagnant going to other uses. And that's a theme that I'll touch on a fair amount more later. On the flip side are the energy requirements of the water sector. And these are driven by the fact that energy is needed both to clean water and to move water around. If you've ever lifted a 5-gallon jug of water, you recognize that water is heavy, and moving it over mountain passes and across long distances can be energy intensive. So the best estimate right now is that roughly 13% of the electricity consumption nationally goes to actually these processes, cleaning and moving water around. But today what I'm going to focus on is the first half of this equation, the water use for generating electricity. So the obvious question is, why does it use so much water? Well, the majority of power plants in the United States use water to generate steam. And that's in this part of the diagram. This steam turns a turbine, and then electricity is generated. But then this water needs to be recondensed, and this requires a lot of colder water to do this. The cooling water, which is represented here in the cooling tower, that accounts for the bulk of the water used by the electricity industry. And roughly 90% of the electricity in the United States is generated through this process. But the specific cooling technology that's employed in any given power point, which is represented by this cooling tower here, that can vary. So in general, there are two main types of cooling. The first, which is called recirculating cooling, and in this type, water is taken into a plant from a water source, and after it's heated, it is cooled by evaporation. Very little of this water is actually returned to the source. Most of it evaporates, sometimes, or typically going through a number of cycles. I think on average it's about 7 cycles through the plant before it's ultimately evaporated. But the point is that very little of it is returned. The other type, called once-through cooling, water is taken into the plant, but then it is directly placed back into the original water source, but at a much higher temperature. On average, that temperature is about 17 degrees Fahrenheit higher than the original water temperature. So from a water quantity perspective, there's an important trade-off here. And that is, for a given kilowatt of generation, more water is withdrawn in a once-through facility, but 2 to 5 times more water is consumed through evaporation in the other. And there are other options here, such as dry cooling, which is where air can be used instead of water. But there are efficiency penalties when you do this, and it's also expensive to do. So you see that in only about 1% of the power plants in the United States today. You can also have hybrid cooling plants, which are somewhat of a combination of the two. In addition to the thermoelectric cooling requirements, there are other water uses in operations. For example, photovoltaic panels require washing, with estimates ranging anywhere from 1 to 26 gallons per megawatt hour. Hydroelectric dams are associated with evaporation, and estimates range anywhere from 0 to 18,000 megawatts or gallons per megawatt hour. But it's difficult to know how to account for this because that water is not only used for power generation, but also for recreation, public water supply, a variety of other sources. So there's accounting issues there. In addition, pollution controls, other processes require water. This ranges anywhere from roughly 10 to 150 gallons per megawatt hour for various cool processes. Now beyond that, if you think about the life cycle of electricity generation beyond just the operations of the power plant, fuel extraction requires water for example, dust control for coal mining or hydrologic fracturing for shale gas. The processing of coal and uranium, such as the uranium milling, enrichment, and conversion, all requires water. And manufacturing, for example, there's special materials required for concentrating solar power and photovoltaic panels. So all of those require additional water use that's not necessarily reflected right there at the power plant. Now, all these different uses are associated with a number of water quality issues, such as temperature impacts and other water quality issues. And I'm not going to get into these today beyond what I just did, but you can look for some related work also in that special issue, as well as a number of other places. So on that, I will take a brief breather to see if there are any questions anyone wants addressed based on this beginning, and to drink a bit of water. All right. My support crew is shaking their heads saying no questions. So moving on, and this is moving into the research that the EW3 group is performing now. So part one of the initiative is focused around establishing this baseline. And it's really getting at understanding how much water is actually used by power plants today. And the majority of this work is reflected in this report, which, as I said before, is available on Union Concerned Scientists' website. So to get at this idea of how much water is used by power plants, we use these data, which were generated by the National Renewable Energy Laboratory, NREL. And so this graphic here shows the range of relative water withdrawals, which are shown in blue, and consumptive uses, which are shown in brown, for different power plant types. And simply put, the water use that you see is a function of both the cooling technology and the fuel type. So using these different coefficients, we were able to estimate water consumption and withdrawals, which I'll be showing you in a little bit. But the point of this is that the relative mix of fuels and cooling technologies, both of those things combined, determines how much water is required to go into a power plant to create the electricity. So for example, if you take existing coal power plants and replace them with natural gas power plants, you decrease the carbon emissions by approximately 50% per kilowatt hour, and you also decrease the water use by approximately 30% per kilowatt hour. In contrast, if you replace a coal plant with a nuclear power plant, you see a decrease in carbon emissions by greater than 90% per kilowatt hour, but you also see an increase in water use by 10 to 20% per kilowatt hour. Finally, and this isn't shown in the graphic, but if you supplement a coal power plant with carbon capture and storage technology, you can decrease carbon emissions by roughly 99%, so there's very little carbon going into the atmosphere. But you increase the water associated with this electricity generation from 35 to 100% per kilowatt hour. And this is driven by a combination of new process requirements and also efficiency penalties. So in other words, the message here is that low carbon options are not necessarily low water. And so these trade-offs are important to consider given the nature of the water use in the United States. So based on what I was just saying in this graphic here, you might expect that it could be relatively straightforward to look up how much water is used and where for power plants across the United States. However, the GAO, the Government Accountability Office, recently surveyed users of federal data on water use that's collected by the USGS, United States Geological Survey, and the EIA, the Energy Information Administration, and found, quote, a number of shortcomings that limit the usability for analysis. And upon this, they concluded that without this comprehensive information, policymakers have an incomplete picture of the impact that thermoelectric power plants will have on water resources, and will be less able to determine what additional activities they should encourage for water conservation. Therefore, as part of the EW3 initiative, researchers built and cleaned a database of power plants from these EIA data. And to this collection of all the individual power plants in the United States, or the majority of the power plants, they applied the water use factors that I just showed, which, based on the technology listed in the EIA data, and this is all coming from 2008 data, and was able to assess the state of the current information. What we find is that many, in fact, the majority of self-reported water use by power plants is outside of expected ranges from published literature, which is shown here in a comparison based on the 8-digit HUC, hydrologic unit. I forget what HUC stands for, but the 8. So the point here is that you see a lot of red on these maps, and red says that the power plants are reporting what is below the calculated values. So 58% of power plants report withdrawal below the calculated values, and 75% are reporting below for consumption. And sorry, I'm getting a little laughter in my audience. It distracted me. So only a small number of these, and these are represented by the green, are actually within the expected value, and that's 18% for withdrawals and 12% within consumption. And this is a very generous range reflected by the large bars in the figure that I showed earlier. So the key point of this is that self-reported data is not very reliable. So if we use this quality control data collected by the EW3 and using the water use factors that I just represented, we can get a better sense of the water use throughout the country. And so these are the information that I'm going to be working with for the rest of the presentation. So this graphic here shows a location of major thermoelectric power plants in the United States. And each bubble represents the amount of water that was withdrawn in the year 2008 by each power plant. And the color reflects the type of cooling that's used by that power plant. So you can see, for one thing, that much more water is withdrawn at once through facilities. You also see that the distribution across the United States varies. So in the east, generally speaking, there's quite a few once-through plants with substantial withdrawals. And just kind of diving in more deeply, in Georgia, for example, about 2/3 of the water withdrawals are used for thermoelectric cooling. In contrast, in Colorado, less than 10% of the water withdrawals actually go to thermoelectric cooling. And in general, in the West, you see many more recirculating power plants and even more, not even more, but more dry cooling power plants. And an important aspect not reflected by this picture, though, is not just how much water is used, but also where is shown, but also what type of water is being used. So this graphic here shows the relative sources of cooling water across the country broken down by water basin. So nationally, and this is reflected in this pie chart, you see 80% of the water used is surface water, and about 90% of this is fresh water. But if you focus on the Southwest, you see a pretty different picture in terms of the water used for cooling. So for example, California uses a lot of saline water. The lower Colorado River Basin has a lot of recycled wastewater use, as well as groundwater. So there's a lot of sources beyond just freshwater and surface water being used, particularly in the southwestern region. And an important aspect of the use for thermoelectric generation that must be considered is the source water and not just the technology being used. So another way to look at this picture of national water use is to consider the amount of fresh water used per kilowatt hour of power generated by an individual state. So across our region, there's a relatively high intensity of water consumption for electricity generation, but roughly average intensity for water withdrawals. And this is referring to our regions, the Southwest, roughly this area. And much of what we see here, reflected in this graphic, is a consequence of the prevalence of once-through cooling in the east compared to the west, where we have a lot more of this recirculating cooling. So this is a common theme of these different types of technology in different areas and them having different implications. In addition, the water use at a power plant is not only driven by this cooling technology, the once-through versus recirculating, but also the fuel type. So use of natural gas, as I showed in the water factors a few slides ago, that is a more efficient technology, so it uses less water. So these considerations play in as well. And the reason that these kinds of choices are important is that the stress that exists in water systems. Water availability is all about interplay of supply and demand. So this graphic here shows where there are imbalances between water supplies, and this is referring to both surface water and groundwater as water supplies, relative to the demands from all different sources. That includes agriculture, municipal demands, as well as the thermoelectric demands that I've been talking about. So when I'm showing these pictures, a lot of them are pretty complicated and might look really small on your screen, but basically I'm talking at a high level and trying to focus on the general patterns. So I hope that you can at least see that much detail on your screen at home. So what we see in this picture here is that yellow and red means that the withdrawals naturally exceed the naturally available supplies. And what that means as far as on the ground, there is built infrastructure providing water storage or transfers in between basins, or additional sources such as additional groundwater pumping, or the use of reclaimed saline or recycled water that needs to be utilized to meet the water demands. And so not surprisingly, you see that much of the stress is in the western portion of the country. And this graphic is important to note, is based on the average water supplies over 8 years. And the reason this is important to note is that surface-wide water supplies are actually highly variable, and the average flows may not adequately characterize the vulnerabilities. So what I'm showing now across the bottom, this is the lowest surface flows, annual surface flows, recorded for each 8-digit HUC region from 1999 to 2007. And as you can see, when you use these lowest flow years, there's generally an increase in the water stress, especially across the west, but also to some extent in the east. And if you take the highest flow years from the same period, you see that pretty much in the east, you don't really run into the water stress very much, but you still actually have a couple regions in the west that have pretty high water stress, and a lot of places that have, moderately high water stress. So the importance of all this is that there's this reliance of the infrastructure and not just the naturally available supplies of how much precipitation is falling in a given year, basically. In addition, if we dive down, we get a little more detail if we break the stress out into the different sectors of water use demands. So using 2005 level demands from the US Geological Survey, we break this into agriculture, municipal, and thermoelectric demands. So what these graphics show, and again, I recognize they're probably pretty small, but what the graphics show is red and blue, the left picture here, shows the proportion of demands that are going to the sector that I'm talking about. So in this, all the red are areas that are, the majority of water that's used is going to agriculture. Now on the right-hand picture, you see the same scale as the same color scheme as what the previous slide showed. And you see the red and yellow, that is areas that are using more demands than the naturally available water in that individual HUC 8 basin. So as you can see, across the vast majority of the West, agriculture is the dominant water user. And you can see one of the important things here is that this is a broad regional issue, and it's something that happens at a large scale. Now, thinking about how these demands might be changing in the future, water use for agriculture is more or less constant. If you look at municipal demands, you see a much larger proportion of the water going to the municipal demands throughout the east. But if you think about where there's less water supply, these come up as water stress, primarily in the Southern California area. And this again demonstrates the reliance on storage as well as imports from the Colorado River. Now, if you look at the thermoelectric, you get a pretty different story. And the main point here is that the water stress becomes very localized instead of these large regional things, such as this agriculture, which is large swaths of red, but you see a lot of individual points on the map. So the water stress from thermoelectric power plants is very localized, and stress can be driven at the local power plant scale. If you see, there are individual points red, so here reflecting the Four Corners power plant in New Mexico, other coal generation in Wyoming. So individual power plants can have a large impact on this national level map at a local scale. So in addition to that consideration, energy is really the only sector with strongly growing demands for water. And given some of the questions about this energy technology mix, it's somewhat of a wild card. So there's the scale is an important thing to remember, but also the idea of the trends that we're seeing of how these different water uses might be changing in the future. And that kind of sets up what the second part, or the third part of my talk today is. But before I go into that, I will take a brief break to see if there are any questions that came up about what I've shown so far. So the question here is, could you elaborate on how you determined that the self-reported data was unreliable? Well, the first aspect of this determination is actually the GAO report. So in 2009, what the Government Accountability Office does is they're brought a question, and they usually go through multiple avenues to get at this information. And one is they actually interview a lot of water managers, a lot of people who would potentially be using the information. And so those people said, streamflow data provided by USGS, that is very reliable and that's very helpful for projecting future trends. But there are some questions about how usable the electricity generation collection water is. So that was kind of the first part that sets it up. But then within the EW3 assessment here, it really came from an effort of pulling together this information from the database. So the EIA, you can access the publicly available information that the power plants provided to the EIA. And so as part of the EW3, this information was collected and then basically ground truthed. So researchers looked, for example, at where power plants said they were, and they just compared, well, is this a place? And so if you use the latitude and longitude coordinates, you find that some power plants are placed in the middle of the ocean, or in Canada, for example. So clearly there's some high-level issues there. But also in this process, what the researchers that were doing this were also doing is they were looking at what the physical infrastructure at a site is. So they were trying to match up, does the cooling technology that's listed by listed on the EIA report, does that match what you're actually seeing? And in many cases it didn't. So there were corrections made along that. And then finally there was this comparison of the reported data to the calculated data. So there are a variety of different reasons. And I'll leave that there, and I'll refer you to the forthcoming paper in Environmental Research Letters if you'd like more information. Or of course you can follow up with me afterwards. So I see now there's an additional question, and this question is, how does nuclear contribute to the carbon footprint? You listed that it had only a 90% reduction. What would be the 10% remaining? And this is outside my expertise, so this is a somewhat speculative answer, but I would assume that there's a number of processes at the power plant that well, the majority of it is actually coming from the life cycle. So if you look at the mining, the processing of the uranium into the fuel, that's where you get. And the construction of the plant, definitely. There's a lot of physical infrastructure there. Yeah, so basically the carbon there, that 90%, that reflects the entire life cycle question. So thank you, that's an important point to clarify. It's not referring just to the carbon that's coming out of the smokestacks. And I see that Paul Davidson. All right, thank you. Any other questions? All right, and my supporting cast will continue to monitor that in case any other questions come up. So now, and I see that I close my window, so give me a second to get to where we are. Okay, so now moving on to the third section of my webinar today, and this is talking about part 2 of the EW3 initiative. So in thinking about the future, we need to consider the future impacts of electricity generation on water resources. So what I'd like to do now is show you preliminary results of a variety of different analyses we're working on, where we're projecting electricity mixes, or we're projecting water supplies out for the next 20 to 40 years, using a variety of scenarios, and then analyzing the water implications of these. So we're taking 3 different approaches to this. And the use of 3 approaches recognizes that there's different types of uncertainty in the trends that we're looking at. So there's uncertainty in the trends of the electricity mix and the way that society decides to get its electricity in the future. There's trends in population growth and what that's going to look like across the country. And then there's also the different trends in what the climate's going to look like over the next 20 to 40 years. And so these are different causes of uncertainty in modeling the future. So we think as a group, we think it's useful to look at these things both in isolation. So if we change just water supplies or just water demands, what is that going to mean? And then also trying to integrate the two to get a picture of what our best idea of what the future might actually look like. And so before I launch in, just want to reemphasize this analysis is preliminary and in various stages of peer review. So if you'd like any of this information, please, we definitely want to share it, but either contact me or the lead author that's mentioned before citing, because hopefully we can get you a finalized version. So with that, I'll return to the same style of analysis that I was talking about before we took the brief break there. And this is based on changing the average water supplies that we see. So many of the impacts that are commonly projected from warming temperatures will be delivered through changes in the hydrologic cycle. And simply, as the atmosphere warms, it can hold more water, roughly 4 to 7% for each degree of warming that we see. So in some places, this will mean that the dries will get drier and the wets will get wetter. Basically, we'll see more extremes of current patterns. But in general, there's a shift in the cycle or in the patterns of water delivery as well as air temperatures. So what I'm showing here is a commonly used data set. This is from Chris Milley and colleagues. And this projects the changes in average surface flows compared to a baseline period. And these are expected changes in the period roughly around 2050. And this is coming from a composite of 12 different climate models. So what we've done is we superimpose these changes on our simple model of water stress that I was just describing. And so what we're doing is we're changing the surface water supplies based on this model. And we're using this to see how the stress changes under the change regime of water supplies. So the graphic on the upper left there shows just the surface water. Down here on the right, you can see that the changes are somewhat less pronounced where you have reliability on groundwater, which is of course what you expect because we're not modeling any change in the groundwater, only in the surface supplies. But this really underscores an assumption to this analysis that there's constant groundwater availability. And obviously this assumption is an abstraction from reality, and there are certain implications of increased groundwater use, such as greater electricity use for pumping, and as well as the potential that we might run out someday of groundwater. So that is an assumption underlying this analysis, and it's just important to recognize that. So what happens when we overlay these changes in surface flows? Well, not surprisingly, you see increasing stress in water supplies where there are projected decreases in surface water. Unfortunately, this corresponds pretty much to places where there's already existing water stress. So basically what we see is the pattern of projected changes in water supplies is going to exacerbate a lot of places with existing stress. And this little tiny map you see here is the one that I showed a couple slides just to get reference of this national water stress picture. So this map here shows the percentage change in water stress associated with this change in water supplies. And if you focus just on electricity generation, you see the stress associated with this electricity generation, again, follows the same pattern you'd expect looking at where you see the changes. Basically, the Southwest, the existing stress that there is going to intensify under these projections. So the second approach that we're taking is by holding water supplies, so the groundwater and surface flows, holding them constant, but instead changing the generation technology mix, as well as some of the other factors such as population growth, and seeing how these might affect the water demands for electricity, and then what that means for the change in this kind of interaction between water and energy. So to do this, we use the National Renewable Energy Laboratory's Renewable Energy Deployment System, called REEDS for short, which projects the changes in electricity generation mix. Now, this model is used for a variety of reasons. One, it has really nice geographic resolution. and this allows the ability to generate results for future electricity generation at a relevant scale for thinking about water. And this is an important point because electricity decisions are often made at state, multi-state, or even national levels, whereas decisions about water use are typically made at the local or watershed level. So again, this kind of gets back to this idea that I was talking about earlier of the different scales for water use, and particularly for electricity generation's impacts on water use, is an important thing to think about. So in addition to having this detailed information on the electricity mix, which comes from 134 different areas for electricity generation, this model also overlays 356 different regions that discuss the wind and solar resources. So this talks about the renewable energy potential that is geographically available in a given area. So it's a very realistic model. And in addition to this model encapsulates transmission issues, integration issues into the grid for wind and other renewables. So I'm not going to get into the details, but please ask me, or you can refer to the paper if you'd like more of those details. But basically, the point is that there's a significant amount of work embedded in this model, and it includes things such as retirements of power plants, where new power plants would be sited, projections of price, capital costs, so a lot of different things. So this complex model of future electricity was used to generate different scenarios of what the future might look like. And these scenarios are driven by different policy decisions that might be made. So in one case, which is referred to as the reference case, you see pretty much existing policies going forward into the future. And what you see is this blue section. This blue section represents natural gas, and that continues to dominate. And you see a modest growth of renewable energy potential, which are essentially these upper things. So you see slight decrease in coal, increase in natural gas, and slight increase in renewables going over the next 40 years. And this is considered what we would see if we don't change any policy. The second scenario is referred to as a carbon budget. And there are no specific technology targets, but just put a carbon budget in place, and this is what is simulated to happen. And you see coal generation drops off, natural gas also drops off, and you get some increase in nuclear, you get some increase in coal with carbon capture and storage, and then you also get a much larger expansion of the renewable capacity. The third scenario is the same carbon budget, but there's specific targets for developing more nuclear capacity and more carbon capture storage. So what you see is essentially 40 years in the future, you see those representing a larger portion of the electricity generation mix than the renewables. And then a final scenario looked at is a carbon budget, but also a higher emphasis of energy efficiency and renewable energy. So this white ghosted box, that represents the demand made up for by efficiency. So that's generation that doesn't need to be met. And you see in 2050, the vast majority of the energy generated, which is the renewable energy target of 80%, is coming from the from renewable electricity. So the point of looking at these scenarios is to get a sense of if, with all these different potential future electricity mixes, which are driven by high-level policy decisions, what is the implication for water? So if you look at a national level, this is what I'm showing here is consumption. On the withdrawal, you see pretty much all scenarios, you see a pretty large drop. And that's because conventional coal in all scenarios is going to be retired and replaced on a pretty large scale with natural gas with different things for the different scenarios. But for all scenarios, there is a reduction. Consumption becomes a little more complex, and that's what I'm showing here. So looking at scenario one, this is the business as usual scenario. You see through roughly 2030, there's actually steady or increasing water use. And this is as coal power plants stay online, conventional coal stays online, there's new natural gas coming in. But then over time, you see coal and nuclear being replaced by more of this natural gas. And that's why between 2030 and 2050, there's a drop in the consumption here. Now for scenario two, and scenario 4, you see more rapid retirement of the coal power plants. And then in scenario 2, you see an increase from 2030 to 2050 from the new natural gas using carbon capture. Because remember, I was saying earlier, carbon capture between the different process requirements and also the efficiency penalty, it uses a fair amount more water. So that scenario would lead to more water use than compared to scenario 4, where a lot of this reduction is driven by the fact that you have more efficiency and more renewable generation. So the water scenario 4, you see a pretty large drop in the water use. And then scenario 3, obviously, is following a pretty different pattern here. And this is driven sharply in the beginning by coal retirement, but then you have an increase in the application of coal carbon capture as well as nuclear. So with this scenario, you actually see an increase in the consumption. And again, the point for the level that I'm talking about this today is that these decisions that we're making today about how we put these policies in place and different generation technologies, we talk a lot about what the implications for the different mixes for carbon output might be, but you also see a very different picture for the water implications from these different things. So in addition to that analysis, one of the papers coming out from the EW3 initiative looked at a regional. So it looked at this electricity mix for each of the individual 2-digit HUC regions. And I won't go into detail here, but basically if you look in the southwestern area, in scenario 1, and so this graphic, it's pretty busy and you might not be able to see it, so I highly encourage you to look for this paper when it comes out. And it's currently in press. But basically what you see, and these little charts here show the mix for each of the scenarios. The blue bars show 2030, the red bars 2050. And this is all showing consumption. So this is showing consumption modeled for the future under these different scenarios. So you have scenario 1, 2, 3, 4 for each of the 2-digit HUC regions. And so basically what you see in the Southwest is that if we follow scenario 1, consumption due to new recirculating cooling in places that currently have either no generation or they're replacing once through cooled generation, you see that consumption is staying constant or even actually increasing. So under this business as usual scenario, you see both at the national level and at the regional level a potential steady or even increase in water consumption from power generation. And I think I will just leave that there. Feel free to ask questions and I can dive in more detail, or as I said, refer to the paper. So the third approach used for modeling this, as I said, kind of integrates both the changing water supplies and the water demand. And it does this through a very detailed model that is called the Water Evaluation and Planning Model, referred to as WEEP. And so what this model is it's at a fairly high level or high spatial resolution. It models a variety of different demands for water, as well as the routing of the water through the network, if you will. So for each electricity scenario, this model is able to model the water deliveries to agricultural demands, to municipalities and industry, as well as even outdoor watering. It also looks at things such as the stream flow through rivers, the deliveries through different canals, and an important aspect that's reflected here that wasn't reflected in approach 1 that I mentioned is the use of reservoirs and storage. So this is very important, and particularly in the southwestern region, is the role of reservoirs for distributing water and for the way that we treat water. So for really integrating how these things might look into the future, this model gives us a pretty good picture of this. And one final note about some of the details of this is that it also includes, as well as the storage, and the routing. It also includes a system that keeps track of the priority system here in the West. So an important note about this is that it leaves the legal priority system a little bit and instead assumes that thermoelectric power water demands are of the highest priority, and they will be met. So the way that this model is being used is saying, well, if we make the decisions to make sure that the power generation is going to keep getting its water, which there's anecdotal evidence suggesting that that would be what will happen in the future. So even though that's not the current legal situation, it's a likely situation. So the use of this model is under that assumption, what is the impact upon the water availability for other uses? So on top of this fairly complex model is an assumption of how the climate is going to be changing. And so, and this model, the climate change aspect of the model affects what the surface supplies are. So we use the Reed's model to talk about how the water demands are going to change, and then this climate signal to model how the water supplies are going to change. So modeling the change in regional average temperature, and this is over the 40 years that are modeled here. And it's, you can see, this is for a specific catchment. So this data was generated for each individual catchment, and you get a warming increase, roughly 1 degree Celsius over the time period, but definitely some fluctuation with time. So you have the temperature, and at the same time, you have a change in annual precipitation. And again, you get a lot of interannual fluctuation, but you see in general an overall trend of decrease in water. And this, of course, mirrors what I showed in approach 1 a couple slides ago of what we expect to be happening to water supplies. And so the results from this analysis are still very much work in progress. So this is just a quick snapshot of what we're seeing. But basically, what I'm showing you right now is the monthly average storage for Lake Mead and Lake Powell, which is the vast majority of the storage in the area, contains capacity for, I believe it's 4 years of the Colorado River flow. So obviously very large storage area and plays a huge role in what we see throughout the whole area. And combining the scenarios that I was talking about in approach 2 with these change in water supplies, you can see that each of the 3 scenarios that I was talking about that involve the carbon budget, in comparison of those versus the business as usual, which is current policies that we see, all 3 of those are essentially stacked on top of each other here, as leading to anywhere from 1 to 2 million acre-feet more available in storage on a monthly average basis among all of those different scenarios than what happens with the current. Now, this scenario 5 is kind of an additional counterfactual, and it says, well, what happens if instead of the current policies and costs that we actually have more fossil fuels being developed? And as you can see, and as you'd kind of expect from looking at the water use factors that I was showing earlier, this would actually lead to a decrease at the end of the modeled period, a decrease of almost 1 million acre-feet less water stored in these dams, reservoirs. So again, this is just a snapshot of results, but this, like everything else, is work in progress that will be represented hopefully in the environmental research letters special issue coming out over the next few months. So to wrap up, just some concluding thoughts and kind of overview of what I hope that you gained from this talk today is that the electricity sector really does use a lot of water, but the context, such as what type of water is used, what else is using water, the policies involved, this context really matters as far as what the implications of that water use is. The technology choices that are available, such as both cooling technology and different fuel types, they can lead to very different trade-offs. And in addition, the demand for electricity, which can be affected by things such as population growth, but also energy efficiency and technology, the efficiency of different technologies, those also have implications for water. And finally, the electricity demands are not only against this context of population trends, but also the climate signals. So all these different factors are interacting. If we focus down into the southwestern region, the low surface flows that we have naturally means that there's a large reliance on things such as groundwater, infrastructure, as well as the use of water-efficient technologies. Projected climate and other trends, such as population growth, are expected to further the existing stresses that we have that were developed in the first place because of these low surface flows. And the path of future electricity generation mixes will impact local water availability, as well as the regional capacity to buffer against additional stresses. So with that, thank you for your time, and I appreciate any feedback or questions. So I'm switching over to the chat. And it would be very interesting and informative to intercompare these energy water development scenarios with the growth scenarios for the more basin-specific Colorado basin supply and demand study. Is there a way to downscale the 4 scenarios to the UC-LC basin scale? And the short answer is yes. One of the great things about this scenario is that the Reed's model is that it allows very focused and very large, in fact, I'll jump back to the map there. It allows a very focused, sorry, a very regionally focused, and there's 134 basins, there we go. Each one of these little units here is being modeled for under these different scenarios and population growth. This model can say what is the expected change in electricity mix over the next 40 years. So it's a very, very regional specific, and that's one of the main research efforts that's going on as part of this larger EW3 initiative, is matching those changes to the scale that water decisions are both made but also important. So thinking about those hydrologic units where water flow both naturally is and also the interbasin transfers. So again, that's the longer version of my answer that yes, there is a way to downscale, and it's wrapped up in some of the information that is being published both in that public-facing Union Concerned Scientist report, as well as these individual research papers aimed more towards an academic research audience.
James, you might point out after this slide, or several slides after the one you just showed, the region, the HUC, I think the HUC2 breakdown, that you've got both upper basin, upper Colorado basin, and lower Colorado basin results shown for each of the 4 scenarios in the lower left.
Yes, that's a good point. For those of you who might not have been able to hear that, Jeff Lucas just pointed out, what I was talking about is reflected in this graphic here. You have the upper Colorado and lower Colorado represented, and each of these individual bar charts shown here reflects in the snapshot in 2030 and 2050 for each of those individual 2-digit HUC regions. And this is the paper with Jordan Macknick as a lead author, where you should look for that for more details. And I see someone's typing. Question: will the paper address the cost and reliability of electricity under different scenarios presented? And again, there's a nice short answer: yes. Yeah, there's a lot of details of this analysis that I obviously very much glossed over here. But a lot of those types of details, a lot of the things that hopefully you'd expect to see, you can see by looking at the individual papers for the different analyses. And I presented these as 3 kind of companion analyses, but they'll all be presented in individual papers. And then that report that's going to be collected for May 2013 should show kind of the interaction of these different scenarios and a comparison across them. You're welcome. Any other questions? And I will see if you start typing. So, all right, someone's typing. When will the paper be published? So there's a number of papers represented here. The first of them is going to be available in December 2012, so a couple weeks, hopefully. And the academic papers will all be environmental research letters, and they'll all be collected there. So starting December 2012, over the next few months, is going to be the rollout of the additional ones. And then that major report that is kind of the synthesis document, talking about it all, that is slated for May 2013. And as I said, there are additional venues where some of the individual pieces are going to be released, such as the AGU meeting and other things like that. Can we get a copy of the slides and where? And so for this, the video will be posted on the Western Water Assessment website very shortly, and that video will show the slides. But the individual presentation of the actual slides, we're going to hold off on that a little bit, just because of some of these being preliminary results. So, feel free to contact me if you're interested in an individual figure or individual information, and I'd be happy to follow up and try to figure out, when things are allowed for release, because I want to make sure the information that actually gets spread out there is, the most up-to-date finalized versions. But that said, the video will be available on Western Water Assessment very soon on their website. Any other questions? You're welcome. All right, great. I'm not seeing any more chatting, so thank you very much for tuning in and for your time. And if you think of another question as time passes, feel free to email me. My contact information can be found on the Western Water Assessment website, or you can contact anyone else that you would normally contact through them, and they can get in touch with me. So thank you very much.